Welcome back. We proved the inverse and implicit function theorems in previous videos. We've seen applications of those in the homework assignment, so see more of them. For instance, to the theorem that says the solutions to ODEs are smooth in terms of the initial condition under certain assumptions. So we see lots of applications, but perhaps the main applications of both theorems in this class are going to be to the theory of submanifolds of RD. So we're going to be talking about objects that lie within RD, which are somehow locally m-dimensional, where this locally will be clarified, well, the locally m-dimensional and C alpha smooth. And these objects are very important in calculus and geometry, all over the place in mathematics and applications. Here in this class, we're not going to do much more than state the definitions, prove a few very basic theorems, give a kind of a hint of what the theory of abstract manifolds is, and finally you'll see lots of examples and theorems related to those. But let's start with a definition. So before we give the definition of a manifold, I want to define what a local parameterization is. So I give you an open subset of RD. Right, well, first of all, there's this object here, M. You should think of M as a surface or as a submanifold, I guess. M is a subset of RD, and I'm looking at a relatively open subset of M. What is that? Is the intersection of an open subset of RD with M. And then an m-dimensional C alpha parameterization of A intersection M is a map from, well, a subset of our M, right? The same M as here, to this intersection. We want this set to be open because we're going to be talking about differentiability of F. We want F to be a continuous bijection with a continuous inverse, and that's a homeomorphism between these two spaces, U and A intersection M. So we want a continuous function that is a bijection. We want it to have a continuous inverse. And as a third assumption, we want this F to be C alpha, as I noted here. So it has derivatives in the sense of Fréchet up to order alpha, and they're continuous. And moreover, we have a condition on the derivative of F at any point x, which is that it's injective. And this condition might sound a bit funny. Well, okay, it's okay to ask maybe that's smooth, because then, you know, we want to look at smooth surfaces, smooth submanifolds. But injectiveness, what does that mean? So let's try to give a geometrical meaning to that, at least some intuition. So the definition is more or less like this. So I have M, I have this A, and here in green, okay, this dashed area here is A intersection M. And F is a mapping from an open subset of RD to this intersection of A intersection M, and it's supposed to be a homeomorphism, so it's continuous with a continuous inverse. It's also smooth, well, except to alpha derivatives, all continuous. And this condition that derivative is injective, basically what it means is that, okay, suppose I have x over here, and I pass a certain number of curves. They're non-tangent, meaning they're speed vectors here. They're linearly independent. So here I'm drawing as if m equals 2, so I have two linearly independent vectors. So what we want is that, and that's really equivalent to what I talked about before, is that when I look at these curves mapped over to the manifold or to M, I want their tangent vectors to be linearly independent as well. So if I have a kind of transversal intersection here, I don't want that to become a non-transversal intersection over there. I want this transversality to be preserved. What I mean by transversality is just that these two curves intersect with different speed vectors. Okay, so that's the intuitive meaning. We're going to see that this property of injectivity of derivatives is going to be fundamental instead of the theory developed later. So it's not a technical condition only. And okay, so I define what a parameterization of an open neighborhood or an open subset of M looks like, right? Remember that because A is an open subset of Rd, then A intersection M is an open subset of M. So what's a manifold? Well, an m-dimensional manifold of Rd of class C alpha is a set of points that can be covered by open sets, by a family of open sets, a collection of open sets, right? So all of the A sub i's are open subsets of Rd. And the assumption is that there exists a parameterization of the kind C alpha m-dimensional for each one of these open sets intersection M. So another way of stating that is to say that M is the union of relatively open subsets, and each one of these open subsets has a C alpha m-dimensional parameterization. This collection of parameterizations, open sets in R, remember these guys are contained in R M, these guys are contained in M, but also in Rd. So a collection of functions C alpha that are homeomorphisms with injective derivatives from U sub i's to A sub i's intersection M. This collection is called an atlas. So that means basically, really, like an atlas is a book that has maps of all parts of the world. That's more or less what it is. Each one of these guys is a map. It's a way to put a coordinate system, an m-dimensional coordinate system, in one patch, one of the patches that constitute M. So, okay, definition, if you have never seen it before, it may sound a little bit abstract, so let's try it on a very simple example. It's a construction that we've seen before of a graph of a function. So I give you a C alpha function from Rm to Rk. The graph is a set of points x, g of x, where x belongs to u. So I mean, if we were to draw this, if this is Rm, this is Rk, so the graph is what it should be. Right, it's a subset of Cartesian product, and we'll always identify this Rm times Rk with R to m plus k, right? So, and that's really simple because here we have m-dimensional vectors combined with k-dimensional vectors, so that's like one single m plus k-dimensional vector. We'll call this number d. Okay. So we're going to identify these guys. I mean, they're isomorphic, but we pretend they're exactly the same, which really is not too big a deal. Proposition: the graph of a function like this is an m-dimensional C alpha submanifold of Rd, where D is the sum of exponents. And the way you prove that is an atlas. Okay, what is an atlas? I take an open covering of M, and for each element of the open cover, I find the parameterization. So it turns out I can take a very simple open cover. It's constituted only of the set, which is, well, okay, it's relatively open, right? And I can take just a single element in the atlas. And okay, here I made a little bit of a mistake. So I want something slightly different, which is a function that maps x to x, g of x. So this is a function that I want here. And we have to check that this satisfies the definition. So we have to check that this thing here gives you a parameterization. So what's the proof that it works, right? So M is a graph G. F takes x and u and maps it to an element of the graph, which is given by x, g of x. So you have to check lots of things. Well, that f is continuous with a continuous inverse. What is f minus 1? Well, let's be careful when we define this. Right, it's clear that f is continuous. So graph of G lives in this space, which is Rm times Rk. And the inverse function of f is simply the function that takes the pair xy and gives you x back. And f minus 1 is, say, 1 Lipschitz, so we can contract distances. And it's clear that the inverse function, I mean, be careful, right? So we need an inverse function for this counter domain, right? So u is injective, but we need an inverse function for this counter domain, which is different from wanting an inverse function for the whole, right? So, I mean, there would not be an inverse function from the whole of RD here to U, but there is a kind of an inverse function where you restrict to the graph. Well, basically it's just saying, okay, to draw the graph, I take the points x and I lift them up to x g of x. That's what f does, and f minus 1 does the opposite. So, okay, f is continuous, a continuous inverse. What does df of x look like in matrix form? Well, notice that it maps x to x g of x. So if you write that in matrix form, of course in column vector form, this would be like I have the elements of x, then the elements of g of x. And in matrix form, those would be something like this. So I'd have a copy of the identity matrix up here, and then I have a second block, which is a derivative of g. Of course, everything is with respect to the canonical basis. Well, you just have to check it. We know how to compute these derivatives in terms of Jacobian matrices. So you just do it, and you check that's what you get. And how do we know this is injective? Well, okay, what are the dimensions here, right? So the number of columns is d, which is m plus k. Here I have, sorry, this should be the other way around, right? So I always mix these things. So you have the identity here, so this is m, the m by m identity matrix, and then you have the derivative of g. And this is, these give you m linearly independent rows. And if your matrix has linearly independent rows, that means that its row space has dimension at least m. That also means that the column space has dimension at least m. However, the input space, right? So the input space of this matrix is m-dimensional. So dfx, if you like, is a linear transformation from Rm to Rd. The input space is m-dimensional. If the output has dimension m, or at least m, then that means that this linear transformation must be injective. Because, you know, we have the column space plus the kernel, the dimension of the two gives you the dimension of the input space. So the only way things can work out is that if dimension of the kernel is 0. And there you go. So I'm using linear algebra here, okay? That's sort of unavoidable at this point. I mean, if you like, you can check directly that this matrix is injective, just showing that if you have a vector here that gets mapped to 0, this vector must be 0. Okay? So we have all the elements of a C alpha parameterization. Well, I should have said that alpha is C alpha because G is C alpha. That's also something you should check. The derivative of f is injective at all points. F is continuous. It's a bijection between U and graph. And its inverse is also continuous, so it's a homeomorphism. And as we said before, that gives us an atlas with one single element to cover the whole graph. So that's the simplest example. Interestingly enough, in some sense, all manifolds are like graphs of functions, at least when you talk about local properties. So locally, a manifold is a graph of a function, except that maybe you have to turn space around or to rotate it or do something funny to it. But it's a graph of a function. We'll get to that later. So the next simplest example of a manifold is a sphere. I'm not going to prove it right now that it's a manifold, but the most classical argument is to say, okay, you have your sphere, you have the north and south poles. Of course, all this works in many dimensions as well. Here I'm doing for d equals 3, right? And you can cover the sphere by two open sets, which are sphere minus south pole and sphere minus north pole. And I claim that for each one of these, I have an atlas. So these are open subsets in the topology of the sphere, relatively open subsets. And for instance, if you omit the north pole, this guy, what's a parameterization? It's just stereographical projection. Take any point of the sphere, like this guy, pass a line through it, going from the north pole up to the x and y axis. It hits this guy somewhere here. So this is P, this is the projection, and our F for parametrization is the inverse of this projection. That's a projection that does not cover the North Pole, but covers all the points. Right, so that's the parameterization for this guy. The parameterization for this guy is just your graphical projection from the top up. You don't have to do it because it'll give a different proof that the sphere is a submanifold. But it's instructive to try and do this. I mean, this is done in many classical books. I'm not going to do it here. Okay. So we've defined manifolds, and I also want to define an important concept related to manifolds, but it's a concept that makes sense for any subset of RD that's non-empty. Okay? And that's the tangent space. So I give you a set S, so this would be S. I give you a point P in S, and I say that a tangent vector, a vector V is tangent to S at P if there's a continuous curve over S that at time 0 hits P with speed vector, right, with derivative vector equal to V. So tangent vectors are precisely the vectors V that you can obtain in this form. Take a continuous curve over S that passes through P at time 0. The derivative of this curve at 0, if it exists, is a tangent vector by definition. And then the tangent space is defined over here. It's just a set of all vectors V that are tangent to S at P. So a simple exercise is to show that the 0 vector always belongs to TPS. So the tangent space is never empty. And why is the 0 vector there? Well, just take gamma of t constant equal to 0 to P, and then you get the 0 vector is a tangent vector. Okay? So the tangent space is never empty, but it can be a very funny set. I mean, if you talked about manifolds before, now you consider these guys are not manifolds. So this is a union of two line segments, this is a cone. You can check that the tangent space at P here is just a union of two lines. So TPS is the union of these two lines. Okay, here I'm just saying that this is 0, right? So, yeah, I mean, shift this guy to 0. These two lines give you the tangent space. Well, the tangent space at this guy, it kind of looks funny, right? So if, but it turns out that tangent space here consists of only the 0 vector. It's a nice exercise to try to do this. If you heard of tangent spaces before, of manifolds before, you've certainly computed tangent spaces for lots of manifolds. These guys are not manifolds, but you can still compute their tangent spaces. So what's special about manifolds, you might ask, if you haven't seen this before? Well, if you have a manifold, it turns out that the tangent space is directly related to your parameterization. And it's actually very easy to write. Here, you're writing it in a more general form, of course. Manifold is covered by parameterizations. Here I'm just saying, well, take a point that's contained in an open set of M, that is A intersection M for A contained in RD open. Take a point that has a parameterization around it, right? A CL for parameterization that's M-dimensional. If you take P like this, then you can compute its tangent space in terms of F. And the way you do it is, you remember, we have this thing here. Here I have a pre-image of P. Well, here I have M, P, and I have this parameterized neighborhood that gets mapped here. So all I have to do is I compute the inverse image of P, which exists because F is a bijection, right? It's a homeomorphism. And then I look at the range of the derivative. I look at all, well, that's a set of all vectors of this form, where W belongs to Rm. Remember that this guy here lives in Rm. So the range of the derivative gives you the tangent space. In particular, the tangent space is an m-dimensional subspace of RD, a vector subspace. So if you have a manifold in particular, this assumption that there's a parameterization satisfied everywhere. All points have some open set around them that's parameterized. And in that case, for a manifold, for an m-dimensional manifold, what you have is the tangent space is always an m-dimensional subspace, which may change from point to point, right? So on the sphere, it's sort of easy to see what it looks like. It's just this tangent plane sitting on a point. Okay, so we're going to prove this theorem. There's an easy direction. So we're going to do it in two ways, right? So we want to prove the equality of two sets. And so the classical way to do it is to show that one contains the other and vice versa. And that's the strategy we're going to follow, except that one direction is much easier than the other one. The easy direction is that the range of derivatives contained in TPM. How do we prove that? So, okay, take a vector v in the range of the derivative. That means that v is the image of some v naught contained in our M by this linear transformation. And of course, right, so let's go back to the world of parameterization. Here I have x sub p. I'm going to try to draw the manifold here with a point p. And this is the set, more or less parameterized by this guy. Here I have my vector v0. I'm just going to take the straight line that passes through x of p. And it's well defined for epsilon small enough, right? It lies inside the set here. U, if epsilon is small enough. This curve at 0, it gives you xp with speed v0. When I map it over by f to the manifold, what I get is, of course, gamma of 0 is f of xp, which is p by definition, right? Remember that xp is a pre-image of p. And gamma prime of 0 can compute by the chain rule. So that's going to be the derivative of f at xp applied to v0, and that gives you v, right? Remember that v0 was chosen to be the pre-image of v under this linear transformation. The upshot is that, as we said, any vector in the range, any vector of this form here, has to be an element of the tangent space. And the strategy is simple. You just draw a curve over here, and it gets mapped to a curve over the manifold. That works very well in this direction. And of course, you want to do something similar to prove the other direction, right? So the other direction is more like this. I have a curve here on the manifold. It has its tangent vector v. I'd like to show that this corresponds, okay, this is p, this is x sub p. I'd like to show that that curve over there corresponds to a curve over here, and that this curve has a tangent vector gets mapped to v by the derivative. So it's easy to carry a curve here to a curve here just by using the inverse function of f. Right, I don't know why you wrote fp. Right, so this would be f minus 1. So the inverse function carries gamma to a gamma tilde in the domain. That's easy. The problem is that it's not clear we keep differentiability. That gamma being differentiable here at time 0 means that gamma tilde is still differentiable at time 0. If we had that, that would be done, basically, as you're going to see. So we need some tool that allows us to make this conclusion. And it turns out that the tool is slightly complicated, so you have to bear with me for a little bit. Basically, I want to invert this mapping from A intersection M to the mapping, from an open set in Rm to A intersection M. I want to invert it with some sort of differentiability. What I'm going to show is that I can, in some sense, so this is M dimensional, this is D dimensional. Well, from the definition, you see that M is D because range, the dimension of the range of df xp is M, and that has to be less than or equal to D because this guy maps R to D. Well, anyway, M is less than or equal to D. So what I'm going to show is that by artificially adding some coordinates over here, I can turn F into a diffeomorphism, capital F. And when I have a diffeomorphism, this operation of taking the inverse becomes trivial. I know I can do it. There's no problem. So what's the statement that we need? Well, that's theorem 2 over here. We're given a parameterization satisfying all those assumptions that it's m-dimensional, C alpha, so it's a homeomorphism with the injective derivative at all points, and C alpha. I gave you a point in this open intersection, and it's pre-image, right? So this should be f minus 1 of p. What I'm going to show is that you can actually, we're going to add coordinates, right? So I'm going to take a subset in a larger, remember this guy's contained in Rm, So I'm going to build an open set in a larger dimensional space by adding d minus m coordinates. And this new open set is going to contain the image of xp, that is xp with d minus m 0 coordinates added at the end. So there's this open set. There's another open set here. And contained in A, right? Remember that we have, okay, we're going to draw this later. An open subset contained here. And there's a diffeomorphism mapping U1, which is like U with some added coordinates, to A1. And here's what it does, right? So if I take a vector of the form x0, so x in Rd with some 0 coordinates added, then computing f there is the same thing as computing little f, right? So here I have big F, and when I'm saying that big F somehow extends little f. And the other thing is that if you, right, so you have here A1 contained in A, so A1 actually intersects the manifold. And, right, well, intersects the manifold because, sorry, this should be A1, right? So because P belongs to A1 and P is in the manifold as well. So if I take a point Q that's also in this open set, the relatively open set of the manifold, its preimage has to have the form x of Q 0. So okay, that may look very confusing and complex. Let's try to see what it means in a picture. So what's drawn in green here, so you have to bear with me, right, a little bit. Remember, what does a parameterization give us? It gives us the following. You have this open subset U in Rm. Sorry. U is contained in Rm. And F maps U to A intersection M. So this would be it. Sorry, this region here. Right, so M is a red line. So pretend the manifold is one-dimensional. So A intersection M is like an interval in M, and U gets mapped to this. So what's the statement of the theorem? Right, so I can find a subset here in Rd, this A1, and I can find this capital F mapping an open set, right, that intersects this horizontal line, right? So remember, this guy here lied in Rm. Now I've added d minus m coordinates. So, and I can see that this blue open set here gets mapped to the blue, right? This blue open set here, U1, gets mapped to the blue open set A1 over here. And that's a diffeomorphism, a C alpha diffeomorphism. So it has an inverse. And now you may ask, well, okay, one open set gets mapped to the other and vice versa. What about the manifold? And I'm saying that all points in red here, all points that already belong to Rm that you just added zeros to, they're still going to be mapped to the manifold in the same way they're mapped by little f. And conversely, if you take a point that's over here in the manifold, inside A1 and in the manifold, you know that it comes from this red line over here. You know that its preimage has the last coordinates equal to 0, the last d minus m coordinates equal to 0. So this is related to a result sometimes called local form of immersions. I'm not going to get into this terminology. To be honest, I don't like it too much. But it's basically saying that if you have a parameterization, then by adding some coordinates, or perhaps restricting yourself to smaller open sets, then you can turn your parameterization into a diffeomorphism. And the diffeomorphism is such that you're still mapping this m-dimensional space to the manifold, and vice versa. Okay? So that looks complex. Let's put it to use before we prove the statement. So how does it give the theorem? Right? So remember that our goal is we have here our tangent vector. V is a tangent vector. And we want to argue that this tangent vector is in the range of df at xp. xp is a preimage of p. So I have a tangent vector. And remember that a parameterization is kind of a restriction of a diffeomorphism, right? That's what theorem 2 gives us. And this open set here, A1, contains P. So by taking epsilon small, we can assume that the situation is as follows. So we have here the manifold, we have here A1. Well, P is in here. And we can assume perhaps, well, just by taking a smaller epsilon if needed, that the curve lives in here. And therefore, I can look at the inverse image of this curve in U1, right? Which is going to be something like this. And of course, U1, remember, is a subset of our Cartesian product, Rm times Rd minus m. So I take the pre-image, right? So capital F minus 1 composed with gamma is well defined. I take the pre-image, and I know it has this form. How do I know that? Well, because the points in the curve all lie in a one intersection manifold. And points in the manifold, I know that the pre-images always have the last d minus m coordinates equal to 0. So points here get mapped here. So in fact, my drawing is not very good. I should have said, I have here, just like gamma lies in this one-dimensional surface, eta is somewhere here. Also one-dimensional. Well, this one-dimensional should really be m dimensions, but you will forgive me for not being able to draw m dimensions. So, okay, what's the point? I can invert gamma by f, and I know that because the points of gamma lie in m, then the inverse points are the form eta of t0. So eta is basically, right, so this should be taken as with a grain of salt, is f minus 1 composed with gamma, except that you have to take a projection here. But let's ignore that. So I know that eta of 0, 0 is f minus 1 of p, which is, well, remember that this is xp gets mapped by f, little f of xp is p, so capital F of xp 0 rd minus m is equal to this. So the preimage of p is this guy. Now eta prime of 0, just from this formula, I can check that if I want to differentiate eta prime, it should be clear that I just need to differentiate this guy, and I have to differentiate this guy at t equals 0, and that I can do by the chain rule. So the important thing is that eta prime of 0 is well defined. And here's what I know. I know that, again, right, so gamma equals f of gamma of t equals f of eta of t 0 rd minus m. So I differentiate both sides. But here I'm going to use the fact that I know that f, capital F, restricted to vectors with d minus m coordinates equal to 0 is equal to little f. So I'm actually differentiating little f composed with eta of t. I can do that by the chain rule, noticing that eta of 0 is xp. And now I get this. So I get the derivative of f at xp applied to eta of 0. So remember, this was the vector v that I wanted to prove that belonged to the range of df xp. And I just did it, right? So I have v is equal to this, which is the derivative of this expression, which is the derivative of this other expression. And this, of course, is the derivative of f at xp applied to a vector, so it belongs to the range. So by using this mysterious theorem that turns parameterizations into diffeomorphisms, I was able to show that all vectors in the tangent space, basically what we did is that they have a preimage under the parameterization, and this preimage is actually differentiable whenever the original gamma was differentiable, right? So a differentiable curve has a differentiable preimage under parameterization. A differentiable curve on M has a differentiable preimage. So, okay. But that's assuming that theorem 2, the mysterious theorem. So now we have to prove it. Let's stare at this statement again. So remember, you have to build the diffeomorphism by adding coordinates. And we want these two properties. All points of the form x0 rd minus m get mapped to the manifold and get mapped just like the parameterization would map them. And on the other hand, inverse images of points in the manifold necessarily have this form with x0 rd minus m. How do we prove theorem 2? Well, we want to build diffeomorphism, so it's natural that we try to use the inverse function theorem, which gives us diffeomorphisms. How do we do that? Okay, let's start with the basics, okay? I'm going to be looking at derivatives in matrix form. I'm not going to repeat that all the time, but you should know that when I write a derivative as a matrix, it's because, well, I have chosen the basis and everything. But yeah, matrices and linear transformations correspond to one another. We know that, if you choose basis. So, okay, we know that the matrix for df of xp is just a matrix with, well, it has to have, what did I do here? It has, yes, so sorry. I always mistake these guys. Yeah, no, that's right. So it has to be a matrix, well, I mean, it's, this is a linear transformation from Rm to Rd. So this gives you a matrix with d rows and m columns. And the m columns are these vectors a sub I belonging to Rd, right? The column vectors of height d. So what does it mean for the derivative to be injective? It means that the column space of this matrix has dimension m. And because you have m columns, that can only happen if these columns are linearly independent vectors. So again, I'm going to be using a lot of linear algebra right now. So I'm using here, this is actually an if and only if. Linear transformation given by a matrix is injective if and only if the columns of the matrix are linearly independent. Otherwise, you're going to have, I mean, that's actually easy to see, right? Because if the columns are not linearly independent, then you have a non-trivial combination of the columns that gives you the zero vector. And that means you have a non-trivial vector in the kernel of the matrix, and vice versa. Okay, but never mind. So I'm going to take that as a fact from linear algebra. Okay, so here I have linearly independent columns. Well, what does that mean? It means that if I have a linearly independent set in a vector space, I can always complete it to a basis. So I can add vectors, right? So new vectors here, such that the whole set of d vectors that I get, the ai's and the bj's, is going to be a basis for Rd. Again, that's linear algebra. And now I'm going to define a new function. And remember, I'm going to be adding new coordinates, right? So this function takes the open set U where f was defined, adds new coordinates here, Rd minus m. Remember, for us, this is the space Rd. So now I have a function for an open subset in Rd to Rd. And that takes a pair x and y here and produces f of x plus a linear combination of these little guys over here with the coefficients given by a y. Okay? F of x, the same guy as before. The guy lives in Rd. Plus this linear combination. What do we have? Well, okay, you have to check this, but if you compute the matrix for the derivative of this guy, well, this is a Jacobian matrix. At the point xp0, well, here are the columns of this matrix. So basically, because the first m variables, they all only participate in this, so the first m columns are going to be the same as the columns of df xp. The remaining columns are the remaining elements of the basis. So we see that we have now a d by d matrix with linearly independent columns. Of course, they form the elements of a basis, so they are linearly independent. What happens when you have a linearly independent matrix with, what happens if you have a d by d matrix with linearly independent columns? Well, that matrix has to be invertible. It just has to be invertible. And that's great because we know that when you have a mapping between Rd and Rd with invertible derivative, it's locally a diffeomorphism by the inverse function theorem, a C alpha diffeomorphism. Here I'm using implicitly that because little f is C alpha, capital F is also C alpha. So we have our diffeomorphism in a neighborhood of this point, mapping to a guy over here. Right? And the neighborhoods of u tilde 1 and a tilde 1. Now, we're very close to what we want because we want f diffeomorphism mapping u1 to u1. Remember, I have tildes now, so I'm not quite there, but almost. And we're going to see that this property here is trivial just by construction of capital F. Remember that f is little f plus some linear terms. The linear terms are 0 when you have 0 over here. So 1 is easy. 2 is not so obvious, and let's see. So we have our diffeomorphism from u tilde 1 to a tilde 1 for all points of the form x0. Just by the definition of capital F, I get little f. And remember, this makes sense because u tilde 1 is a subset of u times rg minus m, and f is a function from u to a intersection m. So this computation here is well defined for any point of the form x or g minus m contained in u1, belonging to u1 tilde. Now, this one property we also want this sort of reverse property. So here we're saying points of the form x0 get mapped to the manifold. We also want to say points in the manifold are always have preimages of this form. And technically speaking, it might be that you don't have this yet. Well, I mean, at least in principle. What we're going to do is, because we only want to prove a local theorem, we're going to shrink the two sets to ensure that this holds. And this is going to be the one point of the proof where we're going to use the fact that a parametrization is a homeomorphism. Therefore, it maps open sets to open sets. How do we do that? Okay. U tilde 1 is a subset of u times Rg minus m, which is a subset of Rg. I want to look at a subset of Rm consisting of all points x, such that if I look at x, 0 Rg minus m, that is, if I add d minus m coordinates equal to 0 to x, I get a point in u tilde 1. Remember that my diffeomorphism is defined here right now. So you can check that Zp is an open subset of Rm, and that's contained the original u. And that, well, that has to be contained the original u comes from this. That it's open, just saying, well, if x0 is in here, I move x a little bit. That's just a tiny perturbation because this point has a protective bubble inside, right? This point here is a protective bubble in here. I can always change x a little bit and remain inside. So Zp is also open. Now, crucially, F is a homeomorphism. Homeomorphisms map open sets in the domain to open sets in the counter domain. Well, technically speaking, it's a homeomorphism between U and A intersection M. So this is an open subset of M intersection A, but because A is open, that's the same thing. So if you like, right? So let's jump to this line here. So if I have a open subset of M intersection A, that's the same thing as an open subset of M. Well, this guy has to have the form M intersection A1 with A1, well, if you like, it would be A intersection M intersection A1 with A1 and Rg open. And I can assume that A1 belongs to A1 tilde. That's a reasoning here. F of Zp is capital F of Zp times 0, Rg minus M. This guy is in U1 tilde, so this guy, the image of this is contained in Fu1 tilde, that's A1 tilde. So F of Zp is contained in A1 tilde, and by taking an intersection with A1 tilde, right, I showed you that F of Zp has this form for A1 and Rg open. And I can assume that A1 is contained in A1 tilde, otherwise I can just replace it by A1 intersection A1 tilde, and everything I just said is going to be still true. Okay, so now I have a set of points here, right? So little f of Zp is equal to M intersection A1 with A1 contained in A1 tilde. So I'm going to take this A1 already defined. Remember, I want F from U1 to A1, which is a C alpha diff U. U1 is just going to be the preimage, right? So remember that F is well defined here. because f was actually defined from u1 tilde to a1 tilde. I just have to restrict it to the subset a1, and they still have a diffeomorphism. So, okay. Now let's check a few things. So u1, I claim that the set ZP with zeros added is contained in u1. Why is that? Because if I take x in ZP, f of x has this form. Remember that you have x 0d minus m belonging to u1 tilde. I have this, and this guy here is f, little f of ZP. So for all x in ZP, capital F computed at x, this point, belongs to A1 intersection M. Therefore, it belongs to A1. If a point's in A1, its pre-image is in U1, and that's how you get this inclusion. So ZP is in here. And of course, I also have this condition that tells me that points of the form x, 0, or d minus m get mapped to the manifold, as I wanted. But remember, I'm still missing the inverse condition. I have to take a point in the manifold and show that its pre-image has this form. Now, how do I do that? If Q is an A1 intersection M, I have to show that it has a pre-image of the form XQ0, zeros. But Q, if it's in here, well, by definition, this is f of ZP. F of ZP is the image of ZP by little f. So I know that if you're in the image of ZP little f, then there exists an XQ in ZP of the form such that it's a pre-image of Q, right? I have this. But I also know that if XQ is in ZP, then and because of item A, ZP times 0 or d minus m is contained in U1, right? So this guy belongs to U1. And therefore, little f of xq is equal to capital F of xq, 0 or d minus m. So for all points in the manifold, their pre-images are of the form x followed by d minus m zeros. Oh, the other properties, I mean, maybe you have to go back to the same of the theorem to check that everything works. But now you're done, because you're saying, okay, points in the manifold have pre-images. Actually, they have unique pre-images because capital F is a diffeomorphism, so it's a bijection. Points of the form 0, x followed by zeros get mapped to the manifold. And actually, they get mapped in the same way that a good old little f mapped them. And we've been able to transform our parameterization into a diffeomorphism by restricting the open sets we're considering and adding some coordinates. And that's it. So this proves our theorem 2, which I recall is this odd-looking statement over here that tells us that parameterizations can be sort of improved to diffeomorphisms if you allow yourself to take smaller sets and to add coordinates. And that, I remember, we used to prove that the tangent space is equal to the range of the derivative, which is a very, very important theorem. And with that, we finish this video. In the next video, we're going to be talking about how you use the implicit function theorem to quickly check that something is a manifold. Thanks.